Okay, so we've seen what buffers are and we've seen how they work, what their function is, but I wanted to talk about how they achieve that function. So we're going to talk a little bit about how buffers work. We're going to do that with our molecule glasses on, right? So we're going to have our beaker, we're going to put on our molecule glasses so that we can see inside the beaker and see what's going on. So we have a beaker with water, it's an aqueous solution, and it's a buffer, which means we have a mixture of our weak acid, HA, which A is shown with the green sphere, and then the H is as usual, it is white. And then in the beaker as well, we have a lot of the conjugate base, A minus, mixed in. Now there's going to be a neutral, there's going to be a counter ion in there as well, like sodium or something like that, potassium. That's floating around, but because that's a spectator ion, we've removed it because it doesn't do anything relevant. And so just like in lab, when you made your buffers, you made acetic acid, that would be, for example, HA here, and you added in sodium acetate. Acetate would be what we're representing as A minus here. And even though there's sodium in there too, we're just ignoring that for now. As usual, we ignore the poor, sad neutral cations, the neutral meaning pH 7 cations that aren't doing anything. So you see we have a mixture. This mixture appears to be 1, 2, 3, 4, 5, 6. There are 7 HA molecules in our little beaker here, and there are 1, 2, 3, 4, 1, 2, 3, 4, 5, 6, 7 A minus ions. So it's an equimolar mixture in this case, just like the one you made in lab, but it doesn't have to be equimolar. It just depends on the pH that you're looking for. You would use the Henderson-Hasselbalch equation. You'd plug in the pH you want, and that would tell you the ratio of acid and base that you need to mix together, right? So it's not necessarily the same, but they're usually pretty close. Okay, so now let's look at our buffer, and let's pretend that we all of a sudden we want to add strong base to it. So let's add some hydroxide to our beaker. Again, it's probably going to be sodium hydroxide or potassium hydroxide, but we're going to ignore the counter ion because it's not going to do anything. So let's add hydroxide, and let's put those in just like that. So we're going to add in some hydroxide. So what happens when you add hydroxide to our buffer is that the component of our buffer that's capable of neutralizing hydroxide will do so. So when you add a strong base, it will react with the acid component of your buffer. So a neutralization reaction occurs where HA will donate its hydrogen ion to hydroxide, and that will convert hydroxide into water. And then HA will be converted into its conjugate base. So now let's do that with our molecule glasses with our molecules, right? So 2 of these HA molecules will donate their hydrogen ion to hydroxide to form water. Now that we have water, we're going to kind of eliminate him because he doesn't really contribute to the pH. So the end result of this addition of 2 molecules of hydroxide is that our conjugate base concentration has increased a little bit, and our weak acid concentration has decreased a little bit. And that will affect the pH a little bit because the ratios change, right? The ratio A minus divided by HA will be a little bit larger now, which means that we will have a somewhat higher pH, which you would expect if you added a strong base to your buffer, but it will just be a tiny bit higher. It won't be a lot higher. If we had added that strong base to a beaker of just water, as you saw in lab, the pH would skyrocket because that hydroxide would not be neutralized by anything in the buffer. Now let's have a new situation. Instead of adding strong base, we're going to add a strong acid. So let's add let's add H plus to our beaker. And again, we're going to add it in the form of an acid. So we're going to add hydrochloric acid or nitric acid or perchloric acid or some kind of strong acid. And so there will be a counter anion in this case, like chloride or nitrate or perchlorate. But we're going to ignore that anion because it's neutral and doesn't influence the pH. So we haven't drawn it in. We're just in some H plus like we see there. Now what's going to happen if we add H plus is that the base component of our buffer, A minus, is going to neutralize that added H plus. We're going to get a new neutralization, a different neutralization reaction will occur where the A minus will bind to that H plus and form HA. So now H plus, it to an A minus ion, and all of a sudden the H plus is gone, right? It's been neutralized by reaction with the base component of our buffer. So the result of this is that the acid, the weak acid component of our buffer has increased slightly in concentration. The base component of our buffer has decreased slightly in concentration, which does influence the pH based on the Henderson-Hasselbalch equation. The ratio A minus divided by HA will go down, which means the pH overall will go down, but just a little bit. So the pH does not change dramatically as you saw in lab. If you add strong acid to a beaker of water, the pH drops by several orders of magnitude. Now another image of buffers is to think of a buffer as a combination, if you look in the middle, of a weak acid and its conjugate base, and they're mixed in some proportion. And so I'm going to use this this picture, and we're gonna do the same reaction that we did before. Here's our weak acid on the top, the red, and our conjugate base on the bottom, the blue, and we're going to perform the reaction where we add hydroxide. So if we add hydroxide, the reaction you see here will occur, the neutralization reaction. HA will donate its hydrogen ion to hydroxide. Hydroxide will turn into the innocuous neutral pH 7 water molecule, and A minus will be formed as the conjugate base of HA. So now you can see that the A minus composition has increased, right? The blue bar is higher now, and the red bar is getting smaller because we're converting the HA into A minus. And now if we continue to add hydroxide, as the conjugate base will increase even more, and then eventually the acid will be completely gone if you continue to add hydroxide. Now if we take the same composition of HA and A minus, that middle representation of our original buffer, and instead add plus to it, so here I'm adding H3O plus. You can add H plus or H3O plus. It's all the same thing, right? And so in this case, we have increased our acid component of our buffer, and if we continue to add H3O plus, we will use up the base component, and eventually we will have all acid. Now the statement at the bottom refers to when the buffer gets to the point where it's all conjugate base or all conjugate acid, then what we say is that we have exceeded the buffer capacity of our buffer. So once you reach the buffer capacity, you can't add any more strong acid or base, or it will no longer be effective because there's no longer one of those buffer components in there. One of them is missing now. So once one of them is used up, it's no longer effective as a buffer. And we saw that in lab as well. When you added a few drops of hydrochloric acid to your buffer, the pH stayed sort of very consistent, and it was effective at buffering the pH. But when you added 10 milliliters of hydrochloric acid, the pH sort of plummeted, and that's because you exceeded the buffer capacity of the buffer. Now if we again put on our molecule glasses and we think about what buffer capacity means, the beaker on the left has a whole lot of acid and base mixed together. The beaker on the right has tenfold lower concentration. So I think on the left we have 1, 2, 3, 4, 5, 6, 7, 8, 9. Yeah, 1, 2, 3, 4, 5, 6, 7, 8, 9. Close to 10 times the number of HA molecules on the left and A minus ions on the left as we have on the right. So if we just add the same 2 hydroxide ions to the beaker on the right, then one of them will be fine, but the other one, so one will be neutralized. Problem is there is still a hydroxide ion left in there, and we can't neutralize that because we ran out of HA. So once you run out of one of the buffer components, the pH will change very dramatically, and that's usually bad for whatever you have in the solution, like protein or DNA. It doesn't usually like extreme pH change. So we've seen that buffers are a combination of a weak acid and its conjugate base. This is the Henderson-Hasselbalch equation in the form that it typically exists in. pH on the left equals pKa. Ka is the negative log of the Ka, and that's the corresponding acid dissociation equilibrium constant for the acid component of the buffer. So whatever the acid is in the buffer, that has a Ka, which will be available to you. It'll be in a table or something. pKa is the negative log of that number, plus the log of the A minus in brackets. That is the molarity of the conjugate base, the base component of your buffer. So in class, in lab, you made a buffer that was a combination of acetic acid and sodium acetate. This would be the molarity of the sodium acetate, the base. And then the brackets with the HA, that's the concentration of the acid component of your buffer. So in the acetate buffer that you made in class, that would be the concentration of acetic acid. Okay, so we're going to look into how to use the Henderson-Hasselbalch equation. Henderson-Hasselbalch equation is based on a typical acid dissociation equilibrium. So here we have a generic acid HA dissociating in an H plus plus A minus. If you write the corresponding Ka expression, right, we have the product of the products in the numerator, and then that's divided by the concentration of reactant HA. Now if we set up an ice table, and we plug in our initial concentrations, and so the Henderson-Hasselbalch equation is based on when we have some amount of acid present and some amount of base present initially. Okay, so this is when we have a mixture of an acid and its conjugate base, aka a buffer, then you would have some value in this I spot, and you would have some value here in the initial concentration of base. So they wouldn't both be zeros on the right like they've been in the past. In the past, we've only been we only looked at the dissociation of HA in pure water, where both of these would be zeros. But now we have a mixture. We have an acid and its conjugate base. So there is an initial concentration of A minus, which I'm just going to use these abbreviations. And then we have plus X's on the right, and we have a minus X on the left. And then we have concentrations at equilibrium of X and X plus A minus and HA minus X for the acid concentration. You plug those into Ka, and that is shown here. Okay, so this is the algebraic expression you would get. Now, if we go on the assumption that X is negligibly small compared to HA and the A minus concentration, then that reduces away to give you just A minus and HA. And now X is equal to the hydrogen ion concentration, which of course is related to pH. So here we're just trying to sort of show you where the Henderson-Hasselbalch equation comes from. So now X is the hydrogen ion concentration at equilibrium, which I'm plugging in here because I want to eventually solve this for pH equals pKa plus the log of A minus over HA, which is the Henderson-Hasselbalch equation. So now if I remember that the lowercase p represents negative log. So if I do negative log of Ka equals negative log of H plus minus the log of A minus over HA, then you end up getting pKa equals pH minus the log of A minus over HA, which rearranges to the Henderson-Hasselbalch equation, which is pH equals pKa plus the log. That's an arrow. We're gonna take it to the next page. pH equals pKa plus the log of A minus over HA. So that just showed you how it was derived. pKa is the negative log of Ka. This is the acid dissociation constant of the acid component of your buffer. A minus is the initial base concentration, and HA in brackets is the initial acid concentration. HA and A minus are a conjugate acid-base pair. It can't be any acid and base. They have to be related to each other by the same equilibrium. HA goes to H plus and A minus. They have to be a conjugate acid-base pair. I think the best way to show you how to use this is to just do an example calculation. I'm going to calculate the pH of a solution that is 0.55 molar hydrocyanic acid, 0.68 molar sodium cyanide. This is a conjugate acid-base pair. So we're going to write the Henderson-Hasselbalch equation down. pKa is the negative log of Ka. Hydrocyanic acid concentration 0.55 is going to go in the denominator. Sodium cyanide is A minus, that's going to go in the numerator. So you get 0.68 divided by 0.55 as that quotient at the end. pKa is the negative log of the Ka of hydrocyanic acid, which we can look up on the Ka table. So that's down here near the bottom, 4.9 times 10 to the minus 10. So we're going to plug that in. Now with the 4.9 times 10 to the minus 10, that's somewhere between 10 to the minus 9 and 10 to the minus 10. So we expect the pKa, like it is here, to be between 9 and 10, which it is. And we just plug the numbers in. Incidentally, here, this quotient you get, because you have more base than acid, you're going to have a quotient that's greater than 1. That's basically going to mean that the logarithm of something greater than 1 is a positive number. And so that's going to add a little bit to the pKa. And so the buffers you guys make in class have an equal molar amount of acid and base, which is why the pH equals the pKa for those buffers. However, if you have a little bit more base than acid, then the pH will be slightly higher than your pKa. If you correspondingly have a higher concentration of the acid, which is in the denominator, you would get a negative value for the logarithm down here, and that would take away from the pH equal to the pKa. It would be slightly lower than the pKa. But that should make sense. If you have more acid than base, then the pH should be lower than the pKa. And then we get a value at the end of 9.40. We end up with 2 digits after the decimal, and the reason for that is because the pH equals, this pKa is going to be accurate to the hundredths place here, 9.30. The 0 is going to be the least accurate, least significant figure, because the Ka is 2 digits, 4.9 times 10 to the minus 10, which means it has 2 digits after the decimal, so it's accurate to that 0. This quotient here, 0.68 divided by 0.55, these are both 2 sig figs, which means that this quotient here is accurate to this 2. You take the log of a 2 sig fig number, that gives you 2 digits after the decimal here, and then that means that you have hundredths place and hundredths place, and that's going to round to the hundredths place in the addition subtraction rule.